All right, so our last topic here for gravitation is gravitation potential energy. And you're like, this is Hume's. We've already learned gravitational potential energy. Gravitational potential energy is just mgh, right? Or if I want to be really particular, the change in gravitational potential energy is mg times the change in vertical position. You're like, I already know this. But here's the problem. We made a huge assumption with this equation. We assumed that g is constant in order to use this equation. So if I'm talking about tossing a ball up from the surface of the earth, when I go between these different heights, g is going to be approximately constant at 9.81 meters per second squared. But the problem is if I'm talking about shooting a rocket into space, and I'm trying to get to Mars, or I'm sending a satellite out to go explore the outer reaches of the solar system like the Voyager spacecraft did, my acceleration due to gravity is not constant while this is going on. So this definition doesn't work. So how to actually derive the universal gravitation potential energy is a calculus project. You'll do it in Physics C. So here I just kind of have to give you the equation. And our universal gravitation potential energy is equal to negative, ooh, that's weird, g m1 m2 over r. So this is very similar to our force of gravity. Our force of gravity is going to be equal to g m1 m2 over r squared. If you're in calculus, you might take a moment and pause the relationship between those two functions and see if you can figure out how you could, using calculus, derive one from the other if you know one. So basically, how could you derive this equation from that equation? You might be able to figure out what the relationship is. Now, basically what this tells us is it tells us that this is an inverse square law. This is just an inverse function with radius. So our gravitational potential energy is inversely proportional with radius. So this tells us that as my radius increases, my gravitational potential energy goes down? That doesn't make sense. Why? No. Well, it doesn't. This actually tells us that our gravitational potential energy still increases. But that doesn't make sense. Denominator, no, how? It's because of the negative sign. So if you were to graph this function as a function of radius, and let's say this is like so you've got like a planet type idea. So this is like the radius of the planet. So there's your planet here. And this is gravitational potential energy. And this is radius r. That what happens is if you were to plot this function, you get a graph that looks kind of like this. Where this is the gravitational potential energy at the surface of the planet. So when you're looking at this, this is by definition an increasing function, but our potential energy is always negative. And our relative maximum over here would actually be 0. Our maximum universal gravitational potential energy is equal to 0. So what happens is as radius approaches infinity, my universal gravitational potential energy comes closer to 0. And this really hurts our brains. But this is under the assumption that we're looking at this force of gravity here, and this force of gravity says the further and further away you are, the closer you're getting to 0 for your force of gravity. And this is also saying close to 0, but while this 0 over here for this one is a minimum gravitational potential, gravitational force, so this is force of gravity. Let's say this is our planet, this is our radius, of our planet. We're looking at R. So our force of gravity would look something along the lines of this. So this is Fg at the surface. And it's actually an inverse square, so it's going to decrease towards 0 faster. This is going to be our maximum, our minimum gravitational force is equal to 0. Okay, this is our maximum force of gravity. So this negative value over here is actually our minimum gravitational potential energy. So just as if I were to toss a ball from the surface of the Earth up, my gravitational potential energy increases the further away I get. But what that means is that an increase in gravitational potential energy, that didn't work out right, an increase in gravitational potential energy means that your gravitational energy becomes less negative or more positive. So this is really, really hard for our brains to handle because it just does not kind of make sense to us. Now, once again, both of these equations only work when you're outside of the Earth. You get different functions when you are inside of an object. What's kind of cool is that with the force of gravity, when you are inside of the object, you actually get a linear relationship where your gravitational force actually becomes 0 at the dead center as well. Once again, you could use calculus to define this, but basically it's linear here because as you move at a bigger radius, more mass is going to be inside of where you're at. So you get kind of this linear relationship. So actually, if I was to dig a hole down towards the center of the Earth, I would have my maximum gravitational force here, and once I got to the center, my gravitational force would be 0. So technically, your gravitational force can be 0 at the center of an isolated object, and also when you're infinitely far away from that isolated object. And you can kind of go with that as you kind of go through. So with the with these equations, once again, they only work when you're outside of the radius of the object. They don't work when you're inside. We're not going to do math when you're inside, so you don't have to worry about that. Conceptually, this is important for that as well. Now, how would we use this? Well, you can just do a calculation of gravitational potential energy. When we're looking at orbits, remember that if you are in a circular orbit, your gravitational potential energy is going to be constant because your radius is constant. So where you might see gravitational potential energy is when you are changing to a different radius. Let's say we wanted to escape an orbit. So let's say that here was the Earth and we had some sort of satellite here. We're just going to have a mass of our satellite, and it's got maybe it's got its own rockets or something like that. Okay, so we've got some rocket orbiting in space, and I want to actually get this object to escape Earth's gravity. I want to launch it so that it escapes Earth's gravity. Well, what's going to happen is at this initial position right here, you're going to be at some overall radius. That radius would be the sum of the radius of the Earth and whatever height it's at. So, you know, it could be at some altitude there, and you've got the radius of the Earth here for that bit. And that is like our initial position. Well, as I launch this rocket, as it moves this way, you're going to increase our gravitational potential energy. And let's just assume that I only have the capability to for the rocket to burn instantly. So I'm not going to have a continuous burn situation. I'm going to be able to get it basically maybe like a catapult. Let's say I had a big space catapult here and I was going to catapult it away. So there is going to be some sort of speed that I need to have at this position right here if I'm going to escape Earth's gravity. Well, where do I have to go to escape Earth's gravity? Well, I have to go to a second position here that it is a radius that is infinitely far away. Well, when I want to escape, there's going to be lots of speeds that I can use to escape the gravitational force. But this escape speed is going to be the minimum speed to escape a gravitational field. So I can always launch an object with an even higher escape speed. Okay, I can always do that. But this is the minimum speed to escape. Well, if it's the minimum speed to escape, if I have even 1 meters per second smaller speed than that, basically I would start falling back to Earth. So if I can't, if I don't have enough speed, I'll fall back. Well, that means that I want to reach this r equals infinity with a speed equal to 0. This is my huge assumption for doing an escape speed type problem. So I'm going to assume that my kinetic energy is equal to 0. When I'm at a radius of infinity, my gravitational potential energy is equal to 0. If I'm at a speed of 0, my kinetic energy is equal to 0. So I'm going to have some initial k kinetic energy here at position 1. I'm going to have some initial gravitational potential energy. So I'm going to have both gravitational potential and kinetic energy. But I want to have no or 0 value of energy at the end, which means my initial total energy here is actually 0, which is where this negative comes into play. So let's take a look at what that calculation would look like. So what would happen is I would say that I want my total energy at the start, so K1 plus U1, to equal my total energy at the end, K2 plus U2, just like we've been doing over and over again. But my K2 and my U2 are both going to be 0. So I want my K1 plus U2 to equal 0. Well, K1 is going to be 1/2 m of the satellite v escape squared. So it's going to be VE squared. So I'm going to abbreviate that as VE because I want to write out escape. Plus my gravitational potential energy is negative G mass of the Earth, mass of the satellite over my radius between them. And that has to equal 0. So basically what this tells me is at this point, my kinetic energy has to have the same magnitude, has to have the same value as my potential energy. It's just my potential energy is negative. So I can see from when I set these equal to each other, I can have 1/2 mass of the satellite v escape squared is equal to G mass of the Earth, mass of the satellite over R. That the mass of the satellite actually disappears. So as long as I'm in an ideal situation where my satellite is not within an atmosphere, so there's no other like drag forces going on, if I am actually in a pure vacuum, then the mass of the object doesn't matter. Now when I'm launching objects into space, obviously you're within an atmosphere, and if you're launching them from the surface of the Earth, then you're going to have a very large atmosphere to have to deal with. But if you could actually fully escape the atmosphere of all the objects in the universe, so basically there were no atmospheres anywhere, then the mass of the satellite itself would have no play. But because we are launching atmospheres, mass is actually one of the biggest limiting factors when we are looking at spacecraft launches. And they have to measure that down to like the milligram, and when they're planning down their masses. Otherwise they might not have enough fuel to reach their destination. It's kind of crazy. So if I go through here and I want to solve for my escape speed squared is going to be 2g mass of the Earth over R. And so then if I take the square roots, I get that my escape speed is the square root of 2g me over R. Now what is this R? So remember, this R is technically RE plus H when I am looking at the Earth. So I'm not going to do that here because we can just use R as our variable, because I've seen something like this before, and I bet you have too. And that is that our orbital speed is equal to the square root of G if I'm looking at the Earth, me over R, just whatever I'm orbiting. So my orbital speed here is square root of g m e over r. If I take the square root of 2 times my orbital speed, that actually equals my escape speed. Oh, isn't that so cool? So there's actually a mathematical relationship between the orbital speed and the speed that you need to escape. So if I was in an orbit here and then I engaged thrusters, I would need to engage thrusters in a way that I reached a speed that was square root of 2 times larger, and then I can escape that orbit and continue on to outer space. So that gives you kind of hopefully an introduction to gravitational potential energy. If you're having a difficult time wrapping your head around this negative, I suggest doing some reading to kind of get a feel for what that negative really means. Like I said, it's due to mathematical definitions, calculus, and so forth. And then escape speed problems are really cool and interesting, and to kind of look at the relationship between our orbital speed and our escape speed. All right, have a good day.